Earthquakes, Part 1. This map represents the most devastating earthquake in our lifetime. It was the 2004 Sumatran earthquake. It started at a subduction zone here at the Sumatran Trench and produced a tsunami that resulted in as much as 227,000 deaths. Luckily, earthquakes of this magnitude are rare. The Earth tends to have about one earthquake of a magnitude 8 or higher a year, and 17 between a 7 and a 7.9. As you can see, the earthquakes that are smaller are much more common. In fact, if you take a look at this map of California, you can see in one typical week we had 400 earthquakes, but all of them so small that it's unlikely anyone felt them. Of course, California has so many earthquakes because it's located on a plate boundary. In this map, you can see the locations of earthquakes as they mimic the plate boundaries, where two plates are either moving toward each other, away from each other, or, as in the case with the San Andreas Fault, two plates are sliding past each other. A plate boundary is responsible for the worst earthquake in the United States. That was the 1964 Alaskan earthquake. It was a magnitude 9.2 and occurred because the Pacific Plate was sliding underneath the subduction zone of the Aleutian Trench. This produced areas that were lifted 50 feet in the air and a displacement up to 64 feet. The duration of the earthquake was 3 or 4 minutes, and that's huge when you consider the Northridge earthquake lasted for only about 10 to 15 seconds. The death toll was only 131. This was due in part because it was Good Friday and people were home, but also because the area was not well populated at the time. Some of the worst damage was done in an area near Anchorage called Turnagain Heights. The housing development was built on top of a layer of clay, bootlegger clay. When the earthquake happened, cracks developed and the entire section moved down toward the sea. The Alaskan earthquake created a tsunami that did damage all the way south to Crescent City, California. The New Madrid earthquake of 1811 was not one earthquake, but a series of 3 to 5 earthquakes of magnitude 8.0 or higher. It caused the Mississippi to change its course, created new lakes, dried up old lakes, and may even be responsible for bells all the way in Boston to ring. Now, New Madrid, Missouri is located right in the center of North America, so it's clearly not on a plate boundary. However, plate tectonics can explain the frequency of earthquakes in this area. It's caused by a failed rift zone. 750 million years ago, the supercontinent of Rodinia was breaking up. Rifts joined each other to make mid-ocean ridges, but one rift failed and became a failed rift zone, located now under New Madrid. It is still there, a broken part of the crust, absorbing the stress of the North American continent moving westward away from the mid-Atlantic ridge. As you can see from this diagram, New Madrid, Missouri still receives earthquakes. It's still active and could yet give us another major earthquake. The greatest earthquake in California in recent history was the 1906 San Francisco earthquake. It was a magnitude 8.3, and 250 miles of the San Andreas Fault moved as much as 20 feet. This lasted from 40 to 60 seconds. The worst thing about this earthquake was the fire that devastated the city. In this picture, you can see an offset fence in San Francisco. You can see that the other side is clearly moved to the right because the San Andreas Fault is a right lateral strike-slip fault. Recent earthquakes in California. In 1971, there was a 6.7 earthquake called the San Fernando or the Sylmar earthquake. In 1989, there was the Loma Prieta earthquake on a small part of the San Andreas Fault. That was a 7.1 and happened during the World Series. In 1992, there was a 7.6 just outside of the Los Angeles area in the desert of Landers, California. And of course, there was the Northridge earthquake, a 6.7. This should lead us to the question, what causes an earthquake? Here's a simple demonstration. As stress is applied, the earth bends and finally breaks. The idea behind this is called the elastic rebound theory. Stress is applied as one plate moves toward another. The strain is the way in which the earth responds. It can start off by responding elastically. Eventually it will fault and you give off waves. Stress, strain, faulting, earthquake waves. Let's take another look at stress versus strain. Stress is the load placed on the material. Strain is the deformation or the reaction of the material to that stress. If, for example, you have a spring, you can add a little bit of stress and it will behave elastically and come back. After a while, however, this stress will be too much for elasticity and it will start to stretch in a permanent way, flow rather than breaking. Finally, it will break. Rocks will also break, and it depends on which rock you have whether it will deform in a ductile manner before it breaks or simply shatter quickly. The fault is a brachial rock along which movement has taken place. Notice that the fault is a plane, a two-dimensional surface along which movement occurs. The movement may start at the focus, but eventually the entire plane moves. To clarify the terminology, the hypocenter is also the focus, is where the movement begins. The epicenter is the place on the surface of the land directly above the focus or hypercenter. The scarp is the cliff that results from the movement of the fault. Here's the scarp that resulted from the Alaskan earthquake. Another look shows you an area before the earthquake where there may be a few small movements of the rock called foreshocks. Then the large focus of the earthquake begins and the otherwise elastic rock starts to tear. After the earthquake, there may be a few aftershocks resulting in small movements at the edge of the fault. To begin with, the stress is at the highest level, so the earth is deformed and ready to break. The rupture beginning at the focus radiates out in a circular fashion. After a few seconds, some of those waves will hit the surface and you see faulting occurring. So it's not like the entire fault moves as two blocks next to each other all at once. The fault kind of unzips along the fault zone as it radiates outward. After a few seconds, the fault has extended until finally the rupture has progressed all the way, it stopped, and the stress has been returned to zero. Faults, however, break the surface. A blind thrust fault does not do so, and that's what the Northridge earthquake was. This pink fault was the Northridge earthquake, and it never came above about 4 kilometers, so there is no scarp as a result. You can see the main shock started just below the San Fernando Valley, so the epicenter is in Reseda, even though it's called the Northridge earthquake. This is a reverse fault, so it pushed upward, and the Santa Susana Mountains, as a result, got pushed about 60 centimeters higher. Although you don't see a scarp, there's plenty of evidence of upward movement, as you can see from these tented driveway slabs in Granada Hills.